Okay. Recording now. All right, Chitar, please shoot your questions. Looking forward to them. Let me share my screen.
Thank you. Sure, thank you. So you were referring to both the binomial distribution and the Bernoulli distribution in, I believe, slide 5.
Yes, I know which one you're referring to. Yeah.
Yeah. So my question was, the Bernoulli distribution, is it just a type of binomial distribution? That's what Open Statistics was saying. Anything else we should know about it?
Bernoulli is basically a single trial. So you're looking at one single trial, and this distributes in a certain shape, and this shape essentially forms then a binomial distribution. But it in the simplest format, it follows a Bernoulli distribution. So it's just you're aiming for one individual one. And this is the probability you mean to model with logistic regression. So this is why it's around the Bernoulli distribution. But the principles between them are comparable. It's just the application is different.
Oh, okay. All right. Yeah. So I was just wondering about that there. And then in slide 9.
Mm-hmm. Yeah.
Yeah, the same. I wanted to confirm the interpretation for beta 1 and beta 0.
Yeah. So this is so now you're looking at something different, right? So you're changing your outcome now. Now your outcome is basically following a Bernoulli distribution, which essentially is not a continuous variable anymore. It's a binary outcome. So you have a 0 and a 1. So that means that basically your estimate from, so you could hypothetically, you could predict 0 and 1 with an intercept, which is at 0 to 1 and just a slope, right? But the way a linear regression would continue, it doesn't have boundaries. So the boundaries of what you mean to predict, that you mean to predict the 1, what you mean to predict essentially is exceeded by the slope, because the slope continues at infinity. So when you have an increase in blood pressure, this will essentially continue until infinity. So for that very reason, you're changing your angle that you're looking at by essentially converting your probability of 0 and 1 to the odds. And these odds essentially are calculated as the probability of an individual event divided by 1 minus the probability. So success versus failure. And by calculating these odds, you're essentially relating the odds that continue to minus infinity and to plus infinity. You're relating these basically to your linear relationship here in your linear regression. So now the problem was that you're running into, and I have a slide here which is specifically looked for you. This is from BIOS620. So this is one of Dr. Wardron's slides. So when you're relating in your distribution essentially that log-8 function between log odds and your probability, with the log odds, you're preserving a somewhat linear relationship between 0 and 1. And therefore, when you convert your odds that go from infinity positive to infinity negative, you essentially can, with the log odds, restrict them to 0 and 1 and model so the probability. And this is what you mean to do by logarithmically transforming your odds by allowing you to essentially relate them to your linear function of a beta 0 and a beta 1 xi, where basically your yi, that is here the odds, becomes predictable using your linear predictors. So that's kind of that relationship that is being lined out here. So essentially you have your y being predicted by a linear regression, by a linear function that essentially relates in logarithmic transformation linear to your odds. Does that explain this slide a little better?
Yeah, that explains it better.
Keep in memory this slide. I think this is really what makes it very clear, because essentially you're transforming it in shape that it gets a logarithmic function where you can relate your probability to your log odds within the framework, ending with 0 and ending with 1. So this is how you can predict your 1, which is your success, whatever the success is, whether it's something negative or something positive, but you can use a linear function to predict the success.
Can I see the original slide, please?
This one? Yeah.
Yeah. So the question, beta 0, how to interpret beta 0. Essentially,
yeah.
that's that's just the kind of when beta 1 cancels out.
Correct. So when beta 1 cancels out, so you have, let's say you have male sex versus female sex. You code your male sex as 1 and your female sex as 0. So you're basically your quote unquote 0 risk is your default risk in the female population, and then not real risk, it's odds, but basically in a multiplicative way, you're essentially adding then these log odds of beta 0. You're adding this additional log odds from male sex, and then exponentiating it to essentially get to the actual odds will essentially allow for you to then estimate the odds in addition to female sex. So this is this slide where we're relating this to odds ratios, right? So basically it comes to this formula. So you have so your xy, where x equals 0, xi equals 0. You have your log of the probability of your binary variable sex being 0 divided by 1 minus the probability of 0. So this is success, this is failure. So you actually get those log odds for your beta 0, which is your quote unquote default log odds. So this is female gender. So, but now if you look at xi equals 1, which is male sex, you're adding here a predicting slope from your log odds, from your probability of 0 to your probability of 1 of success. And you're adding this in a certain way that adds up and becomes then exponentiated and gives you the actual log odds ratio. And this is consistent, and this is this example, with estimating your odds ratio. So you're estimating with some certain inaccuracies, but it's fairly accurate. You're estimating the odds ratio of an outcome happening versus an outcome not happening, or in this regard, comparing treated with control, which is your 1, this is your 0. So essentially your beta 0 is the risk of not having link status and being in the control group, right? So this is your default set. And from that on, you're calculating the odds ratio, the odds ratios from control 0 treated 1. And calculating this in the regular fashion, as you can calculate odds ratios, where you basically divide, so it's kind of a risk ratio, but it's related close to the odds ratios. So you have 1.36 divided by 0.7, you come to 6.77. Analyzing this now with a logistic regression, you come to an odds ratio of 6.77. And these two are consistent with each other. So you're estimating here treatment, and yes, so you predicting your success in regards to treatment, and based on that default odds that you have for your control with no outcome.
So for female and male, which one was assigned a 0 and which one a 1?
Yeah, here not. This was just my examples. Here, this would treated would be 1, link status would be 1. So you're basically you're looking here at 0, 0, that would be this group.
Okay.
Oh, no, it's actually not. Sorry, it's this group. This would be the control group. This is 0, 1, 1. So you basically, this is your reference group. So 0, 0 would be this group, 1, 1 would be this group. So this is success in comparison to non-success to failure.
I see.
Yeah. So these are the corresponding. So you basically calculate this as a proportion of this. So it's basically an event happening in that group versus an event happening in that group. So it's success minus failure in one group, and it's success over failure in the other group, and the ratio between that becomes your odds ratio. It would be nicer to actually spell out the entire formula, and I'll change that in the slide. So, but does this make sense? So it's a calculation of an odds ratio, and you mean to predict this odds ratio by using the same principle in the logistic regression, and you're basically estimating it by fitting it along a linear function, and then relating the probability and the odds to that linear function indirectly by exponentiating and log transforming it. And this log transformation is essentially shaping this in a linear function and allows the calculation with the boundaries of 0 to 1, and thereby allowing to predict a 1.
I see.
So you're forcing it kind of in those boundaries.
Okay. And then the AIC was mentioned, but I was trying to figure out, is a larger AIC showing a better fit, or the other way around?
No, it's the other way around. It's smaller AIC. Oh, the AIC, you're already far ahead. You're already in session 2. You're already in 2 in session 9. Hold on.
It was in 8.
Oh, it was in 8? Really? Oh,
Yeah.
I thought it was
with
the 8. Okay. It was the likelihood ratio test, right?
It was slide 12 in 8.
Really?
You made a comment about it, and it was 495.4.
Okay.
It's written on the bottom of the slide in 8. Yeah. I didn't look at 9 yet.
Oh yeah. Found it. Okay. So essentially, the smaller the AIC, the better the model in general, because it's a sign. I cannot walk you through the details of it. So that's the archaic information criterion, and the competing metric is the Bayesian information criterion, the BIC. So usually you can do AIC and BIC, and you can also take both into consideration. I think BIC acts better with more variables included, and it accounts better for the number of variables in the model. But again, this is something I could not ad hoc explain in more detail. But yeah, the smaller the better. And essentially, if you have two different models that you're comparing, the smaller AIC would be the one that you would choose.
Thank you.
Sure. So what is being done, I hope, is kind of clear. So you are the AIC is, for example, done if you do an actual comparison between two models, and we will get to that. I thought there was in class 9. There's a model comparison. I hope to find it now. Oh, here we go. So that's this is, for example, how you use AIC and BIC in real life. So you would compare the performance of two different models in terms of their explanatory power. So you basically would compute AIC and BIC, and you would see differences, which would make you lean towards one model versus the other. And in an Anova comparison, you can basically compare the prediction of these models, and you can interpret using an Anova with a chi-square distribution, or sometimes also an F distribution, depending on the model at hand. This is chi-square distribution because it's basically categorical variables. So you can, based on this comparison and the corresponding p-value, you can then say whether your models and the prediction of these models are significantly different. And then you would, based on the insight whether they're different or not, you would pick that model for your final analysis that basically presents with the smaller AIC. So I thought you were referring to this. Does that answer your question, Shita?
Yes, thank you.
Yeah, great, sure. Any other questions with the classes? I think class A was considerably easy, so it allows for a good first take on logistic regression, and it gives a first good start. So the key to this class is really the comparison, in my head at least, is the comparison here, where you compute the odds ratio, and you see after computation of the odds ratio, you find an odds ratio that is basically predicting here the success, so having a 1 as the outcome, predicted by different factors, which is here the intervention at hand. So you are then predicting the same odds ratio by approaching it with your GLM. And this is basically, it is the same format as we had for the LM, so for the linear model. It's just the function is now GLM, and you're letting your function know that you're interested in binomial distribution, which consists of individual Bernoulli trials. And you basically can, based on that, then use treatment as a predictor to get here to the log odds. And important is also that these are basically looked at as the so-called log odds. So these are to be exponentiated to essentially get to the actual outcomes. So this is here the log odds for treatment, which is consistent with the odds ratios here. So I think these are the key points that are to be taken home from logistic regression. And this also sets a nice stage to actually use logistic regression then in a practical setting. What else? If you were to calculate other odds ratios, you essentially always need to exponentiate them. Keep this in mind whenever you're interpreting them, and this includes the 95% confidence intervals. So if you, I think at one point in the lab, we're doing also 95% confidence intervals. Here we go. So you would need to also, if you were to calculate it by hand, you would basically add the log odds, the standard error, and the log odds multiplied by 1.96 and then exponentiate it. So this basically would get you to these 95% confidence intervals around your odds ratios. So here was the question about the beta hat 0, so the predicted, the intercept. So this is as said. So this is where you're basically looking at this quote unquote default odds. This is basically where outcome as well as intervention would be 0. And you're basically looking at the default or baseline odds, so to say. Any other questions? Any specific questions? How did the lab go? The Challenger estimate. Did you all have a chance to look at the lab code already?
I looked at lab 8, but the assignment I didn't get to.
Yeah. So the idea with lab 8 is essentially really how to learn how to deal with logistic regression models. So when you are, so you need to adapt here. It's a working directory. So you basically get to the help.rct data frame. You can then create a table, and this table is the same that you see in the lecture. You can use this to build the very same model that we have seen in the lecture. So this would essentially give you a summary fit. And again, I want to remind you that, and as I said earlier, so you basically can with summary fit 1, summary fit, you get always this overview. With ls summary fit, and I'm flagging this because it may be interesting down the road. So you essentially can, you see with summary fit, you see here an ARC, for example, to your question, summary fit, you can always extract whatever you're interested in just easily by adding ls. You get all the sub-objects, and with summary fit $ARC, you can essentially get all these specific aspects. Then in the same format of the linear regression, you can also with plot fit, you can basically do an investigation and inspection of all the diagnostic plots. You can then see the residuals. You can look at the various kinds of residuals. So here the respective diagnostic plots. So these are the residuals that you essentially can now compare between the different estimates. You compare residuals at different levels of the predicted values. You can see now the QQ plots based on your estimates. You can see scale locations between the respective predicted values and your residuals in various fashions. And the interpretation is somewhat comparable to that of linear regression. You're just looking now at a different scale, obviously, because you're predicting here log odds, predicted log odds, what is actually observed occurrence probabilities and odds. Good. Secondly, we have here, in addition to that, we have the Titanic data set. So this was the Titanic data set, which allows you here quite some interesting training overviews. So when you study this, it's actually a very interesting data set. It's really a very nice feature from that package to allow you to look at all these different information of the passengers of the Titanic. You see here breakdowns as per different sexes. You see who survived, who won, who did not survive. So you see survivor as a function of gender, and you can with summary fit, you see how that related, and you see that there is an improved, so when you male, you have a higher survival advantage, which is not necessarily. Okay. So as a actually surprised, I thought actually that women had a higher survival on the Titanic, but it seemed to not have been so. So you see negative log odds. And negative log odds always indicate here kind of a protective direction, a protective trend. So you basically see that male sex associates with a protective effect. So males had an increased odds of survival. Good. So this was the lab, and then essentially you have in the answer key is basically the approach shown already. So you basically you read the read XL package in. So you have to install this package. Then you can read in the data. You get an overview of the data. You see the different temperatures, and you can, based on the temperature, you can associate temperature with damage. So what you see here, that when you visualize it, so here's the with function with challenger. You plot temperature as a function of damage. Actually, no, damage is a function of temperature. So damage is 0 and 1. So this is a binary outcome. And you essentially, you plot manual axes. So side 2 indicates the x-axis, whereas side 1 indicates the side 2 indicates the y-axis, ranging from 0 to 1. Side 1 indicates the x-axis with basically from 50 to 85 in a sequence of 5. So remember this sequence function. We talked about this, right? This basically allows you here. So if you look at the sequence function, you see here by 5 is 50, 55, 60, 65. You can basically plot a manual kind of function allowing for you to customize your axis. So here 50, 55, 60, 65. So it basically follows in 5 increments of 5 degrees Fahrenheit. Was it Celsius? I think it's Fahrenheit. So then essentially you're asked to build a logistic regression model that basically will be called FIT. It's again, it's GLM, that's a function for logistic regression in combination with familiar binomial. And you're modeling damage as a function of temperature. You get a summary. And that summary allows you then essentially to predict your outcome. With the predict function, you can utilize the underlying model, and you can then customize what temperature you're interested in to model. So if you model, oops. Oh, it's the wrong fit. So now you're building the model. This is the updated model. And if you model it now with a temperature of 31, you find the predicted odds of damage. So if you change this temperature now, it will basically utilize your temperature. So the question was to predict the probability at a temperature of 31 degrees. And if you were to use a different temperature, you just need to change that. So with 80 degrees, for example, the odds are substantially lower. So this is basically how you use the predict function. We've talked about the predict function already. So this is now just another application. So basically these models perform all in the same way and fashion, and they can be used in more or less the same way and fashion. It's just important to understand the substantial differences in interpretation and differences in terms of the arithmetic underlying basis. So, any other questions? Tracy, Daryl, any questions concerning anything relating to class 8?
I joined late, so I'm sorry if you already went through this. In the lecture 8, slide 14.
Slide 14, yeah.
In the lecture, I didn't hear you answer the questions that was on the slide, so I just wanted to check if it was important to know. I'm guessing the answer is that we didn't have to check for normality.
Yes, correct. Yes, we
Okay.
don't have to. Yes. So it's also you mean to you predict a 1 in a binary distribution of your outcome variable. So you either have 0 or 1. So for that very reason, the normality is not to be checked because you're log transforming it, and the prediction essentially becomes a function of the log odds. So therefore, the normality is not to be checked. because it is by default, it's not normally distributed.
Right. Okay. And it's the same for the constant variance too.
Correct. Yes. So there are no assumptions to be made in that regard.
Gotcha. Okay.
Any other questions? We can also chat a bit about class 9 already, or we can also leave that. So by the way, for class 9, or for the next review session, so to say, I apologize in advance. I actually meant to squeeze in a review session for Wednesday, but now my flight got canceled and I'm flying now a day later, so I'm going to be in here still at the time. I meant to do the review session. So I hope it is somewhat okay for everybody to do it Friday at 5. So it is 11 p.m., but I'm gonna in Europe, where I'm gonna be, but I'm gonna give my best to be in my best shape. But I'd be happy to go on. I will be online. Please join if you can, or post questions to the discussion board, which I will talk about. I know Friday at 5 p.m. nobody's too keen on biostatistics, but I'm trying to make myself available as good as I can, despite my trouble. Any questions concerning anything? Do you want to have a look at class 9, or do you first want to digest it?
I'm going to look at class 9, you know, if everyone else is.
We can do that. Okay, so let me pull up class 9. Oops. Oh, yeah. Okay, so class 9 basically focuses now on interactions. So you need to keep in mind that sometimes variables do interact. And the example that, so first interaction, so interaction in regression models. Then secondly, it's about how to handle interactions and also how to employ likelihood ratio tests. And this is what I alluded to before when she told us the question on the AIC. So essentially, a likelihood ratio test is comparing different models and allows you to find the most appropriate model. And then also talks about the handling. Once you find a significant interaction, how you're going to deal with that and how you're going to move on to stratified analysis, which is particularly for randomized controlled trials, something that is often found. And there are some remarks on interaction, which is three-ways interaction and relation to prediction. Simpson's paradox, which is kind of interesting. So I hope you're going to enjoy this class because it's quite important what you learn about interactions. They're quite often found. So we talked about linear and logistic regression. So essentially what you see, you're always assuming that this prediction that is caused by or affected by your predictor X, xj, is independent of other covariates. Actually, often note collinearity and two parameters paralleling each other and having very high correlation is not a necessity for interaction. So it's not necessarily that they are interacting well just because they're correlating, but in many cases they do. So collinearity is actually something that is quite problematic in analyses, because if you include two collinear variables, essentially that affects your interpretation substantially and can basically dampen it and make your effects that you mean to see entirely go away. So it's really important to test for interactions, mainly those that are biologically related, and you know that there's a biological relationship. So the example that Professor Sang has here included is the age-related increase in systolic blood pressure. And you will hear me talk in the video about it. So essentially, women and men tend to have different dynamics in terms of blood pressure. Men have higher blood pressure at an earlier age, whereas women tend to have lower blood pressure pretty much all the time until they come at a certain biological age where hormonal status, etc., change, and then their blood pressure kind of kind of aligns more with that of man. So there's a different kind of dynamic they have over their lifetime. So that means that there's an age-related change, difference in age-related changes in systolic blood pressure. So this is basically being included in this analysis that Professor Sang has here included in the slides. So you have a situation that either X2 is dependent on, or not dependent, but associated with X1, or you have an alternative situation where X1 is essentially, or the effect of X1 on Y is dependent or kind of associated or affected by X2. So it's important that you keep in mind when you look for interaction that you understand which one is essentially the study variable that you're interested in. And this one you will essentially treat with increased attention in your analysis. So this will also affect, for example, which one you define as your outcome variable, or which one you will define here as your 1 versus 0. So it sometimes makes a difference in which angle you look at it. So if you want to define, for example, an increasing effect, it always makes sense that the one you assume to be lower for whatever reason, you essentially you code that one as 0. Whereas when comparing it to that you coded as a 1 basically shows an increasing effect as an actual positive coefficient, which for that reason it makes interpretation sometimes easier. So essentially you have now an X1 and an X2, and if you want to add an interaction term, you essentially have X1, X2, and X1, X2 interaction term that is essentially here determined by a coefficient beta 3. So in essence, the coding would be done by age, male, and that interaction term. So there are various ways how you will find interaction terms being included. This is just one of them. You sometimes will also see a multiplication sign, so like an asterisk. You will also see an I and brackets, parentheses, sorry, an I and parentheses, and the two interacting variables included in these parentheses. But yeah, so this is the one that Professor Sang chose for this slide. And what you see here essentially is interesting. So you see without and with interaction for linear regression. So you see here the standard linear regression. But you see how this effect is magnified as soon as this interaction term is being included, because now arithmetically this has an entirely different shape. And I'm flagging this example and other examples of the very same kind for exam 2. So essentially you're looking at a constant. So this is your intercept. You're adding to this intercept 22.809, which is your coefficient for male, where male sex is coded as a 1. So you add 22.809 multiplied by 1 plus a 0.731 minus your interaction term of 0.398 multiplied by your x1, which is age. So essentially this will affect your interaction term, and you're basically getting them to 110.01 plus 0.33 multiplied by your x1, which again is age. So this is how you arithmetically would approach interaction terms. In the example where you have a continuous and binary variable, and this essentially changes overall the slope in this association, this prediction of your yi. So if you predict systolic blood pressure, this clearly changes here the slope for females that basically has a more steeper incline, but starts at a very lower level. Hand in hand with what I said before, that females tend to have changes in blood pressure at a later age, whereas men start higher, but their increase is somewhat less steep. So is this clear so far? Any questions? Does this make sense?
It does make sense. I mean, for right now, I understand it.
Okay, good. And this is basically what it is, because it's the interaction. So you have different ways of looking at these interactions, and you have different applications for your interactions and interaction terms. So essentially here we're coming to the example where you have categorical variables. So, and here the interpretation is somewhat comparable. So here we have a logistic regression where we're trying to predict hypertension as a defined blood pressure of greater than 140 millimeter Hg. So essentially you mean to predict this elevated blood pressure by using education. And if you remember our education example from a previous lab, we have no high school degree, we have high school degree, and we have college degree. Yeah. So you're predicting it in the same fashion. So again, if somebody has, I think the reference value here was, I'm trying to remember what the reference value was. We can look back. This is the Simpson paradox. So we essentially were meaning to look at male EDU. So if we look at the contrasts of Here it comes. All right. So here we have our actual packages. These are the fits. So now this is with and without. So this is the blood pressure as a continuous model. Oh. That's interesting. There's something wrong there. That's only coming out correct on the. Not good to show. So this is the blood pressure as a continuous variable here with the lines implemented. So this is what we've seen before, right? This is this plot. Again, in terms of the coding, basically we're taking a subset that is, and so the is NA exclamation mark is NA indicates that you want a subset of enhance, which is not NA, for your variable BPXSY, which is your systolic blood pressure, and you have those with no missing ages and no missing data entries for the male, for gender. And you're plotting it with that line, and you're employing here, after building the models, you're employing the lines with the legend being indicated here. So these codes are valuable, possibly for your research notes, so keep those in mind. Then we have here the definitions. And if we are doing now contrasts to this, that should give us contrasts of enhanced EDU. That should give us the contrast. So we're basically having here's the reference group. This is no high school, no college. So this is our reference group. So when we are looking now at fit 3 and summary fit 3, which I hope will be somewhere here. So again, let's go back here. So we have here no college, no high school is our reference. So we're looking at those with high school having a lower blood pressure, whereas those with college degree having even lower blood pressure. And here, the interpretation of male and the interaction of EDU2 and EDU2 is that they have, once they're male, they have higher blood pressure. So essentially it shifts that slope upwards and it gives them a steeper slope. So basically it kind of attenuates the decrease per se. So it attenuates the decreasing trend with increasing levels of education. So I think that's kind of interpretation to that. So it will affect the slope. So when you see, when you would include here for male, you basically would have a male has a lower blood pressure now after accounting for education. If the individual is educated, has a lower blood pressure. But if you add the interaction term between male and education, you get a shifted increase over time, because those with no education would start at a higher level and would only have a more modest increase over time. But basically, the interaction is then being included in the estimate. And this is what we're doing here in lab 9. Not here. Oh, no, this is a different example. Then lab 9. This one. I don't know what's the link size. Oh, look at that. I think I mislabeled some of these labs. So also please note that if you downloaded already your lab 9 and made a modification to the lab 9 RMD file. Let me find this one.
Well, I haven't downloaded it yet. I only downloaded lab 8.
Okay, great. Yeah, here we go. Because I have the same mislabel mistake here with lab 9. Here's the lab 9. Okay, here we go. Okay, so let's load this. Yeah. Okay, so this is the fit of our blood pressures. So if we're binding this now together, you basically get a plot where you compare 1 and 2. You compare here the blood pressure as a function of age. You get a summary of your fits. And you basically see that the interaction term is here at the 22.87. And this is consistent with what we have seen earlier. We have seen this, what was that slide? Oh, yeah. So this is consistent with this model, essentially to look at. So we're seeing here comparable coefficients, and here we're Stargate, so we're getting this depicted in the same fashion as on this as on the slides. Then we can build here this this analysis, which we've seen already. So that's again, so this is again the same as we've seen in the slide. So this is the example now where we're looking at education. So here we're seeing this is the factorialization. So we're making education a factor, which, as opposed to the previous slide, if you really want to play around with it a bit, you can define the labels in the proper way. So you have the levels: no high school, and college graduate. And you can, with these fits, you can basically now fit through the very same model that you have seen on the slides, which you see here. Until Stargate is computing this. So you basically see here these predictions. So now in the comparison with your ANOVA, you're basically doing the same as you've seen in the slide. So you basically see this comparison. So you see that if you would do AIC fit 3, you see an AIC of 3366 was AIC fit 4. You see that inclusion of an additional term and inclusion, it comes back to Shital's question from earlier. I hope you can all see that. So she asked before, and I think Tracy and Daryl joined after, whether a lower ASC is a better fit or a higher ASC is a better fit. So you can see here, if you are adding additional variables, it's a bit like the R-score. No, it's not, I don't dare to say that because the arithmetics between ASC are much more complex. But essentially, if you add additional explanatory variables in a model, your prediction becomes more accurate. And so in real life, you would essentially compare both models by comparing them in a likelihood ratio test, which in this case here you use the chi-squared because it's only contain dichotomous categories of variables. And the ASC would guide you to select the most appropriate model. So this being said, based on that, you would then, in a further step, so you have an interaction is significant, the model with the interaction is more appropriate. Well, although the ASC is not that much different, but it is significantly different. So you would then, in an additional step, you would do a post-stratification analysis. And I mentioned this, and I think it's important to understand that because you find that often in the context of randomized controlled trials. In randomized controlled trials, you would include intervention, yes, no. So let's say you're testing a new blood pressure lowering medication in addition to an existing treatment for an hypertensive patient. And you're adding this, and you have then a randomized controlled trial where you have an intervention, and the intervention then in your coding is 1, whereas the standard of care, the previous care, would be coded as a 0. So you would then include an interaction between your treatment and whatever you think may have affected your treatment. Let's say you would have assumed that gender does have a permissive effect, or sex has a permissive effect on the effectiveness of your intervention. You would include an interaction term between male and your intervention. So imagine that this education variable here would be intervention. And once you know there's a significant interaction, which you would test then in your ANOVA, where you test the initial model without the interaction and the modified model with the interaction term, and you find a significant effect, and this p-value is smaller than 5%, or whatever threshold you determine, most likely will be 5%, you would then go on and do subgroup analyses. And this is in randomized controlled trials. Statisticians that analyze randomized controlled trials would discourage you from doing that because it lowers the power. This is already what Professor Sang is alluding to here. So it's essentially, you're only restricting and you're restraining your model to only these subpopulation. And you're doing this at the cost of your statistical power. Particularly for randomized controlled trials, this is quite debatable because you have conducted power calculations that went a lot of money into the conduction of this trial. So it comes at a price, right? And this price is power. So only if you're really certain that you have a significant interaction that affects your treatment effect, you would include interaction. That you would go after the inclusion of an interaction term towards the pathway to include subgroup effects and study those subgroup effects in the stratified analysis, the so-called post-stratification analysis. Oops. Okay, of course. So this is how you would define the subsets. And once you have these subset at your disposition, you can then create different models allowing for you to analyze this data separately and to compare all 3 models. And this is essentially your stratified analysis and gives you an estimate for each of your groups. So here we go. And this is where the RCT comes into play. And I leave this to you to play around with that because we're at the end of the hour. We can talk about it longer if you're interested. But I just want to be conscious about time. So we have the remarks on interaction that Professor Sang meant to make is that 3 factors is kind of quote unquote an overfitting almost of your models. So it is sometimes you could do it, but it's rather something that is a rarity. It's also in terms of interpretation, you can just let your imagination flow how tough and difficult the interpretation of such a model will be when you have 3 different interaction terms. Also, it's important to keep in mind interaction is by no means, just like correlation is not causation. Interaction also does not necessarily mean association or correlation. So this can also be variations that are independent, but only in the model interact with each other. And it does also not mean that this is a biological interaction, also needs to be kept in mind. Yeah, so interaction in RCTs, and I alluded to this, that essentially will allow you to design subgroup analysis that are sensible and are of interest. And you are creating a population heterogeneity, which is basically an exploration of a covariate guides you towards what variables are potentially interested in your analyses, in your post hoc analyses. So you will always use a stratified in a primary analysis where you basically have the overall population. And then in a second level, so these are usually predefined. So you usually, RCTs are analyzed very rigorously, following an analysis plan that is usually already has been existent since before the trial even started. Of note is like, for example, if you propose an RCT to an NIH, you will need to have a very solid analysis plan already in place that you propose actually, and you will state to the NIH that this is exactly the analysis that you will conduct. And in a second line, then for secondary analysis, that's when you can go on and test for variations in the covariate, how this affected the overall population, how this performed, how your intervention performed in some certain subpopulation. So this is, it's interesting to look at, sometimes very insightful. Some secondary analyses have been groundbreaking, to be honest. And so it's just, it needs to be kept in mind. They come at a lower power, and the primary analyses are not always including interactions, at least not second level interactions. Sometimes interaction can be part of the primary analysis, but they're not always part of the primary analysis. So this being said, so this RCT example actually nicely outlines what is being done. So you create with the link status with the help RCT file, you're creating a model, including treatment and substance abuse. So you get here estimates for treatment, and you get substance and cocaine and substance heroin as your actual predictors. So if you look at contrasts, you essentially see that treatment 0 is your reference value. If you run contrasts on your substance, you see that your reference value is alcohol. So you see cocaine and heroin in reference to alcohol. And this is basically how you will go on to complete your entire assignment, which essentially is to fill out this table. So you are testing link status with the covariate treated versus control, and substance abuse, alcohol, cocaine, and heroin. So you will do that first without an interaction. So you have control versus treated. Then you have treatment versus control, which is the comparison, the risk, the difference in the odds. And then the same for cocaine, heroin. And then you're using this in an interaction. And the interaction term is essentially built here, just built here. So this first table command is essentially just building the skeleton of your table. So this is the skeleton for, oops. Okay. Well, I guess I got another skeleton already. Okay, so you're getting here already all excluded. So this is the answer here. Okay, so and the table with interaction is, oops, is essentially built here with this. So you have your model one, you get the coefficient out. So if you look at summary model one, so your coefficient here is minus 0.006. So if you look at summary model one, you see that this is the estimate for substance cocaine. So essentially you are on table row 1, lines 3, 1, 2, 3. So this is cocaine. This is the estimate for cocaine, which you pack in here. Then you have your table. So you have table 2, 2 minus table. Okay, so you have 0. You have your sum unnamed summary model coefficient. So this coefficient is basically your estimate for alcohol, which is here. You're basically building out. You want comma ones. This is basically your coefficient. So you're filling this with your entry 1, which is essentially, no, not this one, this one. So you basically have treatment without any interaction with the substance. So you're filling then up the difference, which is basically 2, 2. This is 1, 2 minus this. So you get this difference now calculated. And by that, you essentially get to building this up, which is your substance cocaine. And the difference between those basically gets you then to your T versus C. So this is treatment versus control. So this is basically how all of these cells are to be interacted, and then finally you come to the final result, where basically you have control, treated, and this constitutes the difference between treated versus control. So this is the increase in the odds compared to control. So in the same fashion, you would do that for cocaine, and you would also do this for heroin. And heroin is, I believe, not yet included here. Yeah, so you have something to complete yourself. That's good. Okay, so heroin is still to be done. So same with interaction term. So essentially, you have here the same overview, but it includes now this time around. It includes this and the interaction term, and you will need to get the respective estimates directly from your model. So this being said, so this is the lab that would need to be done. So the heroin remains to be done. So so for those that want 2 points, they need to complete the heroin. Good. So we have interactions cause confusions, and this is the last thing of the remarks that Professor Sang was including is Simpson's paradox. This is literally an epidemiological artifact or statistical artifact in data, where basically you have seemingly that two relations in the relationships in subsets show an increasing trend. But once you build a model on the overall population, because of the differences that they have in terms of starting point and in terms of overall level and the overall means and their slopes, you basically have analyzing this in the overall population without an interaction term and without considering that there are differences between the sexes, you will see a decrease in the overall population slope. So the example here is from a publication that's also part of the lecture. So where you see a decrease if you model this through the entire population, whereas you see increases for both. I'm trying to find the actual data. No, it's just a slide. I thought it was the data. No, that's a pity. So where you but what you see is the overall population shows a decrease, whereas the individual slopes within the groups show both increase. So this is kind of paradoxically, it's not paradoxically arithmetically, but it is paradoxical when you think about it just for a second, and you hear about it for the first time. It's just important to keep in mind that subgroup analysis really serve a purpose and are really important to be kept in mind. This emphasizes the importance of interactions in the greater picture. Okay, so any questions? Tracy, Daryl.
No, I don't have no questions, Professor. You said a lot. I'm gonna try to look at the recording of this, and I know you said heroin is an important thing that we need to focus on.
Yes, so the heroin at the table needs to be completed. So that's to be kept in mind for this lab. So please make sure to complete it before.
Okay.
Look at it. Okay.
Professor, sorry.
Yeah.
I don't have questions about this, but if you're able to stay on after this, can I ask you a question regarding the research note?
Oh yeah, absolutely, not a problem. Okay. So if no further question, then we can conclude the review session for today.
Okay, Professor.
And I hear you again on Friday.
All righty.
Thank you.
All right. Sounds good. Bye-bye.
Bye-bye.